Welcome to Physical Memory Forensics for Files and Cache with Jamie Butler and Justin Murdoch.
Okay. Hi. As she said, we're presenting on physical memory forensics, focusing on files and cache. First, a brief introduction. There's Jamie Butler here. He's the Director of Research and Development at Mandiant. He's focused on host analysis, operating systems research, and he's done a lot of research on rootkits and low-level systems before. I'm Justin Murdoch, currently a student at RIT, but I will be graduating in August, and I'm on co-op right now at Mandiant, working as a software developer on their enterprise product. Basically, going to go through an introduction to traditional forensics first, kind of background information, talk about previous techniques, and follow up with kind of some issues that are existing in current tools used for memory analysis. So mostly what is wrong with them right now is they miss some specific data in files. And also they are misattributed the data that is found. So mostly memory tools right now focus on getting files out of memory. So we're going to speak about cache and reconstituting files out of it, kind of talk about applications of our new research, and then show some demos of the new techniques that we have. We will be releasing a tool, and then at the end we're just going to wrap up with some talk about future work that needs to be done in the area. So for traditional forensics is kind of focused on two primary components, obviously the disk and memory. So disk has really been what has been focused on for the most part. Most tools for forensics target the disk and contents, the files existing on it. It wasn't really until recently that memory was approached as a tool for forensics. So the problems with disk are that the average disk size in a forensics case is just growing exponentially. So memory is a great way to triage a host. It's relatively small, and you can find a lot of useful information in it pretty quickly to give you the best foothold in a forensics investigation. So programs that you're looking for have to be executed, therefore have to be loaded into memory. And in almost every case, attackers overlook the footprint in memory because it's just been too overlooked so far. And in fact, many of the artifacts that the kernel uses to load programs and data into memory that have to exist for the program to run, we can use in our memory forensics to determine more information about them. So memory is comprised of two pieces, userland and kernel memory. This talk is going to focus on userland memory because most of the attacks out there are in userland memory, just mainly because it's easier to get execution and it's more resilient to coding errors. So basically, if you have a problem in your code running in the kernel, it's going to completely crash the system. So the user land is usually where attackers go. Most memory forensics tools have focused on process reconstitution. So given a memory image or just the memory of a running system, most tools out there today try and just recover all the EXEs, all the DLLs, possibly data files as well. So the way that these tools work focuses on virtual address descriptors, which are structures in memory that describe the memory addresses being used for that specific process. And they contain these points here. So here's just a graphic of VADs and kind of a VAD tree. So they contain a pointer to the parent and basically the content of the virtual addresses and the size. So to look for these VADs, most tools scan physical memory for a e-process block, and this is where most of the information is. This describes each process loaded into memory, and basically they locate the directory table base in the e-process so that they can accomplish virtual to physical translation from the process's context of addresses to the actual addresses in memory. In the e-process block, they usually look for the VAD root, which is the beginning of the tree that describes all the processes' address space in virtual memory. And they just enumerate the VAD tree to discover all the virtual addresses. So another approach that has been used in other tools is to basically brute force the entire virtual address space, given a starting range and an end. They just try and grab the whole address space. And on 32-bit systems, this isn't really a problem, but on 64-bit, the limit is just so high, it's really not practical. Also, virtual addresses could be global, so this kind of leads into problems where you might misattribute data to a specific process than another one.
So I'll discuss the first issue with this methodology. Basically, the methodology, again, as Justin mentioned, is to start with a beginning virtual address, translate that into its physical page, and then operate on the contents of that page. So that may mean writing it to disk, or it may be inspecting the page for byte patterns or other things. But we're missing a lot of data if we just translate over the VAD address space. What will happen is a lot of the VAD address space represents files that are mapped into the system process space. These files are EXEs and DLLs, so they're pretty important to us, especially when we're looking for attackers to figure out what is going on in the system. Now, since these are what's called a memory map file, they're shared across address space. So in other words, if NTDLL is loaded in memory and that is in every process address space, there isn't a physical copy of that in every single process. It's a shared memory region. Although it's shared across all the processes though, the page, what's called the page table entries for that particular virtual address range isn't filled in every process. So there may be bits and pieces that are marked as valid and we can go get the data, but the vast majority of that range is actually a null PTE entry. So there are no artifacts describing where it exists in physical RAM. Here's a quick example where we've taken the HoneyNet Project Challenge 3 from about a year and a half ago. We tried to acquire the Acrobat Reader process from that image. So this is an image given to you, and you can actually recreate this at home. I've acquired the Acrobat Reader using the traditional approach. There you see in the table I just chose like 5 DLLs at random to acquire out of memory. There in the column file size and bytes is how large these files would be on the file system. Then the bytes that were acquired with the traditional approach of just using the ranges and the page tables in order to do the translation. You'll see there how much of the file we could recover from the image. In the case of NTDLL, for instance, there was 42% of that file was in memory and translatable using the traditional methods. Now, if we use what I'll talk about in a moment called file objects and some of the structures that they represent, you'll see there we could get actually 55% of the file out of memory. So a little bit better. And this was not using any disk information whatsoever. Another thing that Justin pointed to earlier is misattribution of data. So Mandiant does a lot of incident response and forensic work, and we're very concerned about, is the host compromised? But beyond that, you need to know, which process within that host is compromised? Because as you drill down on the initial infection and so forth, you can begin to build what we call indicators of compromise. Indicators of compromise describe how you might look for that data on other systems. So with a process, once you identify a particular process is infected, there's a lot of metadata that comes with that process. I've just listed a few things here. There'll be like a creation start time, basically when the process was created. You might be able to use that for timeline analysis. Also, there's the username associated with the infected process. So you may suspect that your domain credentials were basically compromised. So there could be people logging in with legitimate user credentials, spawning processes, so on and so forth. So you want to gather all that metadata about the infected process. Also, its location on disk that can feed back into your IR process. So as we find things in memory, remember memory is a triaging methodology. So we triage the situation. We get pointers from memory, typical memory, maybe 4 gigs these days. So that 4 gigs will tell us about 4,000 locations perhaps on the file system that we care about. Well, that's good data to have because on a file system, we mentioned it might be 250 gigabytes of a hard drive and have, over 100,000 files. So if we can start narrowing down on which ones to focus on, that's useful. Well, if we can't attribute the data to the correct process, then that's a problem. So files that are in the cache, for instance, those are global addresses, and they'll translate across any process. So here's a diagram taken from Mark Rosanovich and David Solomon's Windows Internals book. If you don't have that, I encourage you to buy it. It's very useful for doing memory analysis. But here you see this is a representation of a x32-bit, so 32-bit system, and its virtual address space at C1000000 is the beginning of system cache. So what is system cache? That's where the operating system is going to opportunistically kind of load things into cache, expecting that you're going to access it again in the near term. So let's say your program reads a page of data or a couple pages of data, well, they are going to assume that you're probably going to read more nearby. So they'll load up actually more than you requested into memory, into the cache, for future reference. So that just speeds up I/O. When this gets loaded into cache, it appears to be in the process address space of every single process. So if you were just brute forcing address spaces, you would actually acquire the cache for every single process. It would appear that that file exists in every single process, and that's an issue. So let's talk about more effective ways to use memory map files and also the cache. Well, file objects represent both the memory map files, so the DLLs and the EXEs that are in memory. Excuse me. They also represent the some of the data files that are in memory, such as Word documents and PDFs. PDFs would go in the cache. Word documents go in a separate place that we'll talk about in a moment. As we mentioned, the VAD describes the virtual address range that that file occupies. But if it is a memory map file, or if that file is represented on disk for that region of memory, there will be a pointer within the VAD to a control area. The control area will then contain a pointer to a file object. And the file object contains a lot of useful information for us, including the device name. So you can get information like hard disk volume 1, which is commonly referred to in most systems probably as C:. You can do that lookup. Also, it'll contain the file name. So in this case, Windows System 32 Windows /System32 /kernel32.dll. And then the file pointer or the file object contains a pointer to 3 other pointers that is going to describe where the data for that file object resides. So that's what we'll cover. Here's a graphical representation of how it looks, basically in memory. We're going to be concerned here with the data section object, the shared cache map, and the image section object. So for the image section objects, they represent binaries in memory. Image in this case, that's how Microsoft refers to a binary, as an image. If you were using WinDbg, it'd be marked as an EXE, but it could be a DLL or an EXE. The image section object pointer is actually a pointer to another control area. That control area has a pointer to what's called a segment object. And then that segment object, if you wanted to do some sanity checking, would point back to the control area. So if you were scanning physical RAM for these things, you could do some sanity checking on these segment objects and control areas. Also, the segment object will contain the segment size, which is the total size that that file object represents, and the total number of PTEs. So if you would take the total number of PTEs, multiply it by 4K or by 1,000 hex, that should be equal to the segment size. Then the next thing that's of particular interest to us are what's called subsections. So every single, how many people here have opened a PE file in Lord PE or PE view or something like that? You've seen the different sections in the file. So those different sections within the file might be the .text section or the .data section, .resource section, different things like that. It has a relative virtual address within the file, so it's an offset within the file. It also contains a size, and it would describe the permissions or the flags on that area of the file. So when the Microsoft loader loads up that file into memory, it would read that data, and allocate a subsection for each one of those sections within the PE file. We found that the subsections are immediately after the control area in physical or in virtual memory that you then translate into physical memory. So that's how you find the first subsection. The subsection is going to contain a pointer back to the control area, so you can use that again as a sanity check. Jump to the last bullet there. Every subsection contains a pointer to the next subsection. So once you find one of these things, you can walk the list to find all of them that represent the file in question. But then one of the things we're going to drill down on here is every single subsection contains a pointer to what's called the prototype PTE array. So prototype PTE array is basically every entry within that will be the physical address in memory where that page resides. If the prototype PTE array entry points back to the subsection, so instead of a physical address, it actually contains a virtual address back to the subsection, then that sector is paged out. So it's paged out, but it doesn't go to the paging file. Because it's a memory map file, these files are backed by themselves. So the operating system doesn't waste the paging file with this data. For memory map files, especially for binaries, they're not supposed to change. If they do change within the process address context, then the process address gets its own copy of that page, and therefore it would be in memory or it would be in the paging file itself. However, if it's just a binary, it's not changing, the code doesn't permutate, there's no reason to write it to the paging file because every single process will share the same data and it can be located on the file system itself. So in TDLL, if there's a page of memory that is in NTDLL that isn't in memory, it won't be in the paging file, it'll be in the file itself. So there you see within the subsection is the number of full sectors that represent this subsection, or that this subsection represents, and then also the number of PTs that this subsection represents. Now PTs represent 4K pages, but subsection or sectors on the disk represent 512 bytes. So the loader has to keep track of, there could be 2 PTs in use, but only 13 sectors. So when you're parsing these things, you have to take that into account. Here's a graphical representation of that. There you see the control area. We follow it to get to the segment object to do some sanity checking. Once we have a valid control area and segment, then we'll parse the individual subsections to get to the prototype PTE arrays. And once we have that, we can get every physical page in memory that represents that file. Now, the second of the 3 pointers that were in the file object that we care about is a data section object pointer. The data section object pointer we won't go into a great deal of detail about because it's exactly like the image section object. The data section object, though, represents data files in memory. I'm not sure. I'm sure there's certain APIs that you would call that would automatically create data section objects, but I just haven't had the time to research that yet. However, we did notice in our research that Word documents appear to be represented as data section objects. So all I can say at this time, at least, the performance of Word documents in memory should be equally as speedy as the performance of accessing data in EXEs and DLLs on the Microsoft operating system, because they have the same structures. So instead of your file going to cache like a PDF would, Word documents, other Microsoft Office documents, they go into a data segment section object, which performs a lot better than the cache would. And we're going to show you how you can use this in a moment. So the third and last thing in the file object is a pointer to something called the shared cache map. So the shared cache map represents the file data that's in the cache, in the file system cache that the operating system keeps. So this data usually is not as robust when you're doing memory forensics, because it's up to the operating system what it puts in there and how long it stays, and so on and so forth. Plus, it'll also depend on what's going on in the system. You know, if a lot of other I/O is in use, your file may not be in cache, or the file you care about may not be in cache. Also, the size of the cache depends on the amount of memory available in the host. So this isn't the most reliable source of data. It's kind of hit or miss whether something's in the cache. However, it is something that we should be parsing in order to get out any value that we can. So the shared cache map would contain the file size on disk. It would also contain the valid data size that's in the cache. So even if your file is 40 megs on disk, maybe only 100K of it or so is valid in the cache. So that information is contained in the shared cache map. Also, for sanity checking, your valid data size should never be larger than the file size itself. We've seen some structures as they get deallocated and so forth, where the valid size is a very big number and it's obviously greater than the file size, so you just throw those things away because the pointers and so forth aren't going to be useful. Also within the shared cache map is the main crux of where the information is contained is stored in a VACB. So that's a virtual address control block. Each VACB represents 256K of data, which will contain a pointer to the virtual address where that 256K resides. So you translate that virtual address and then you get the information you want. Basically, these VACBs can be, there's an array of them. These arrays can be nested. I encourage you to read Mark Rusanovich's Windows Internals book. I think it's chapter 13 or so. It's all about the cache. There he describes the fact that this layering of VACB arrays can be no deeper than 7 levels, and that's based upon the math around the file size. The maximum file size is 2 to the 63rd power, so that gives us 7 levels deep. I'll let him explain it to you in his book because he could do it more elegantly than me. But basically there's a formula for if you want to calculate the levels, the number of depth of this array tree, you could do so given the file size. Here's what basically a 2-level deep array in the cache map would look like. So an array of a VACB array that points to a VACB array that points to the actual VACBs that describes the data in the cache. So let's talk a moment about the applications. Well, first of all, when we're reconstituting processes, we should probably not only just focus on the VAD tree that's hanging off the process block, we should also focus on the handle table, perhaps, because it's going to have a lot of useful information for us. We can acquire things out of the handle table by parsing the file objects. So file objects, again, are found In the handle table, there will be a pointer to what's called the object header for that file object, and then we can just parse the file object itself and use those 3 pointers that we just talked about. Also, the VACB tree, or the VAD tree, if you recall, has a pointer to the control area, which has a pointer to the file object. So that's how we find file objects within the process context of whatever process we're analyzing at the time. And one of the applications of this is the Windows registry hives. So that's very useful when doing some traditional forensics on a host. The Windows registry hives are contained basically in the system process. It has a handle to the hives. So if we are parsing the handle table and acquiring the process or the system process out of RAM, we can also get the majority of the hive data out of RAM as well. Another thing that may be there is PDFs and other data files. So we haven't spent a lot of time on this yet, but we have discovered some PDFs and so forth that are in the cache. You can pull those out of RAM. You may or may not get anything useful, right? It's just a piece of the file. It's probably not the whole thing. So you're kind of hit or miss on the usefulness of that. Another application that we have is hashing. So I know in computer security world, hashing is a bad word and everybody laughs at it. And I've probably spent a fair share of time bashing it as well. However, I mean, we have over 2 decades probably of hash data. We might as well use it for something. So we can use it to whitelist process address space, so get rid of data that we don't care about, data that belongs perhaps to the operating system and so forth. There's been some research into this field of study. Basically, the problem, though, when you're trying to apply it to memory forensics is that the whole file, or in the past, we couldn't get all the data, so we can never make the hash match, right? Hash on disk doesn't match hash in memory because you have big holes in your data. Well, if we use, sorry, to back up a moment, some of the previous techniques have tried to get around this basically by taking pieces of the file that we do have and hashing. So let's hash a subsection of the file that we find in memory, hash the same subsection that we find on disk, compare the two, and make an inference that, oh, these things must be the same. Now that has a few problems. One is that we don't have the historical data, right? So yes, hashing pieces of files is good. Fuzzy hashing is good. It's also, you could consider to be kind of a subset of that. But we don't have the historical data. So no one's really standardized upon a fuzzy hashing method. You know, you can't go to Bit9 or the NSRL, I don't believe, and get a fuzzy hashing list for your operating system. So we can't often utilize it unless we have a gold master of our enterprise and we know what everything looks like. Another problem that you'll have with that is, since you're only looking at a piece of it, you know, other pieces within the file could have changed. So that may cause you to draw some incorrect conclusions. But if we use these section objects, we can get a lot more data out of the file. And in fact, if we are running on a live system where we can access those pages that have been paged to the file system, right? So NTDLL got one of its pages got paged out and put back into NTDLL. If we can use NTDLL on the file system to read, you know, those 1, 2, 3, whatever number of pages that have been paged out, we can reconstitute the whole file using memory and some of disk. And by doing that, we can hash it all. And therefore, our hash in memory will match our hash on disk. And we've implemented this in future versions of our tool We'll call it MEMD5 because it's based on memory. Peter Silverman gets credit for that name. So after whitelisting, what else can we do? Well, we have a lot of tools out there. A lot of people have begun to apply antivirus type of techniques to memory in order to utilize all this intelligence that we have thus far. Some of the things that people have begun doing on disk is there's classification tools out there. So VX class that was offered by Dynamics before it was purchased, and other automated classification tools put samples of malware into families. So they look at how much of this malware is related, and they'll put it into a family. Well, that, and also there's things, how many people have heard of ClamAV? So it's kind of an open source antivirus. ClamAV also has byte pattern signatures that they generate. So with VX class, they'll take everything that's in a single family and they'll generate a byte pattern that matches all the samples within that family. ClamAV is just identified certain byte patterns that exist for certain types of malware, and then they search disk for it. Well, since we can reconstitute the EXEs and DLLs in memory better, then we can more effectively apply these techniques to memory. So I'll go through some demos. I apologize, I'm going to have to use some canned analysis that basically we've ran because each demo takes about 6 minutes to run on this laptop that I have today. But basically with our tool that we'll talk about in a moment, it's called Memorize. And we're putting these features into Memorize so that if you wanted to, let's say, acquire a process out of memory, you could do so with process DD, and then you just give it the PID that you want and the input file, so like what memory image you're using, and it'll pull that process right out of memory. In this example for the registry Hive information, again, I'm using the memory image that was taken about 1.5 years ago by the people for the HoneyNet project, Challenge 3, and I'm going to look at the system process. So here's what I get when I acquire the system process out of memory. Every place you see a VAD, that is basically a region of memory that doesn't have a file object associated with it, so it doesn't have a name, maybe it's part of the heap or something like that. We just give it the address range that we found it in, call it a VAD. Every file that we get, we give it its name. This is encoded, basically, so we can use things like C:/ blah, blah, blah. And then up here, you'll see, here's the registry hives that we are able to pull from memory. If there's a page in the cache that's not present, obviously we don't know where on the file system necessarily to go to read that. It might be kind of useless to read that out of the file system because this is a cache file. It could be changing what's in memory versus what's on disk. So we're just going to write basically a page of no ups there. So a page of 90s just to keep the linear consistency across the file. If I go to Access Data's tool, their registry viewer tool, I'm going to open up those hives I just acquired. So this was the system acquire from the HoneyNet challenge. Should sort by size. Get something, let's go to system, and it opens right up, no problems within the registry viewer. Then you can use all your traditional registry analysis techniques against this, right? Now we're just back to some of the traditional forensic stuff. You'll still have the last read or last write time of the keys and so on and so forth. So you can do that. Another thing that we did before we came out is we had a Word document open in a newer version actually of Microsoft Word, but the Word document is backwards compatible. We acquired that memory image, and then we ran our acquisition of WinWord against that. So if we go back to our file system, WinWord, the memory image was a Windows Vista machine. Microsoft Word is called WinWord in that OS. Here is the Word application that we acquired. Right now, I believe it's sorted by type. So again, you see a lot of the VADs that we acquired that we don't know what they're doing, but we could inspect those. Sometimes when you're doing memory forensics, you'll send those VADs to VirusTotal or other things, like if you suspect that there's binary code in there, and then they'll tell you whether any AV triggered on it. I've acquired some processes out of memory, and then you can actually launch the process from the acquired directory, which is kind of cool. Here is the Microsoft Office document that was acquired. I'm running Office 2007. It's complaining about the structure of the document, but I'm going to say go ahead and trust it anyway, even though the structure is a bit corrupt. So here's the white paper for this talk. The whole thing is there. This white paper is also on your conference proceedings. And then the last thing I'll talk about is data reduction. So how many people here have ever used AutoViewer? A couple of you. Basically, Memorize is the free tool that we released that does memory analysis. It's the engine, and AutoViewer is the analysis UI component of it. So Memorize will generate a bunch of XML. Everything it finds in memory, it's writing out to disk as XML metadata. And then AutoViewer will give you a visualization of that data. Here we have, I've double-clicked on all the processes. So this is all the processes on the system. And then I've clicked the DLLs tab. So I see basically every DLL or exe that's loaded within the host. Now, this doesn't include drivers. There's a different way to go about getting drivers. We'll talk about that in a different talk. But if you're doing live analysis, so you have access to the file system, and you can get then the correct MD5 and get it to match the MEMD5 to match what the MD5 would be, you can do data reduction. So here in AutoViewer that we'll be releasing in the coming weeks, we're going to say filter on known MEMD5 hashes. Now, what are known MEMD5 hashes? Basically, you have to build up a list of known good, right? So you need a good whitelist to start with. You could use the NSRL perhaps. We didn't get a lot of results with that because there weren't a lot of the files that we were looking for within it. You could build your own whitelist, so you could build your own from a gold master or whatever of your enterprise. Or you could have a co-op that will run these analyses across tons of Microsoft Windows installs and get basically a whitelist or a hash of the native OS installation for you. This doesn't include right now, we don't include third-party applications just because of the time involved. We haven't gotten there yet, but you would want to include known third-party applications that you're running. Let's say Adobe Acrobat Reader, iTunes, things like that. Also, in this example, AutoViewer has the ability to reach out to bit 9. So send the hash to bit 9 for bit 9 to tell us whether they've seen it or not, right? That requires a username and password, like you have to have an account with them, which we don't have right now, so we're just going to say cancel. So it's working. It's finding a bunch of NTDLLs and so forth. They're already in the cache. Didn't find anything in the NSRL of this example, and we weren't reaching out to bit 9. So now that we've done this, we'll right-click again and say filter trusted or ignored modules. And then that gives us a list of the things basically that it doesn't know about. So there wasn't an infection, well, there may be infection on this host because it's a case study from some training that we do. But what we've taken is, several thousand things you have to care about in the form of DLLs. If you reduce that, if you look at a typical, Windows 7 box perhaps, you're going to find, if you accumulate all the processes together and count all the instances of NTDLL and so forth, and all the other DLLs and EXEs, you're going to get something on the order of probably a little over 4,000 files. Well, if you get rid of redundancy, you're going to get that down to about 1,500. If you then apply a whitelist, you can see here that we've reduced that down dramatically. So what we're doing, we're going from 4,000 to 1,500, maybe to 40 that we care about. And that makes the incident process a lot quicker. So as I mentioned, there will be a release of Memorize 2.0 coming up in the next few weeks. We tried to get it in for this, actually for your conference proceedings. We just ran into a couple bugs unrelated to this that we need to get ironed out before we could do the release. So look for that in the coming weeks. It's a free tool, it's closed source, but it is free. And AutoViewer will be released at the same time to make use of this. It's a free tool and is open source, is written in Python. It's not the prettiest UI you've ever seen, but it's pretty useful. There's a link for the free tool, and also check our blog. We'll announce it there when it comes out. So in wrapping up, I'd like to talk about some further work that needs to be done. Basically, one of the first things we noticed, and we're not really sure if this is particular to our configuration or what the deal was, but caching on a Windows 7 system, on my Windows 7 and some 2008 that we tried, 64-bit, the machines that we were looking at had a lot of memory. So we're talking, 16 gigs, 32 gigs of RAM. And when we tried to acquire the system process, we didn't get any Hive files. So no Hive files came out. However, there are Hive files in memory. We could validate that. We could search basically physical memory for the indicators of the Hive, and we could find it. So we then used Matthew Sweesh's tool to convert the memory image into a DBG file that we can load in WinDebug. Load it up in WinDebug. WinDebug has a command called !file cache. And we use that, and WinDebug said there's no caching enabled in this file system. It's basically invalid. So we're not sure if there's something particular about the configuration of the host or something unique about the cache. But basically, we haven't found the registry hives using this method on Windows 7 or Windows 2008. There's also address space layout randomization. How many people are familiar with that concept? So when the binary loads into memory, well, when it's compiled, it says, I would like to be loaded at this address. And a lot of things within the binary are based upon that desired load address. If the binary is not loaded at that address, then the operating system, the loader, has to utilize a section of the PE file called the relocation section. The relocation section is a fix-up, basically. Says, if you didn't load here, here's all the places that you have to go fix up. So this doesn't occur very often in 32-bit OSs because Microsoft likes to load where they request to be loaded, and other applications do as well, unless there's a collision. So typically you won't have that problem of the binary not loading where it requested. However, when address space layout randomization is in use, which is the newer 64-bit platforms, then the loader is going to move that binary around. So it's not going to be at the same static location. Because of that, if there was relocations to do, the OS have made those changes, and therefore the hash in memory won't match the hash on disk. Now, we can reverse out that because we can, if we run the live memory analysis, we can see what the PE says it wants to load on disk. We know where we found it in virtual RAM, so we can go through the relocation section ourselves and do the fix-ups and feed that into our hashing function, and then our hash should match again. And that's what we intend to do, but I don't anticipate that coming out for the next couple of months, just because this isn't the only thing that we work on. Also, something that we discovered in doing this is in some PE files, if they're signed, they have a security directory in the PE structure. So when you look at the PE header, you'll see a security directory, and on older versions of the OS, there were artifacts in memory. So basically there was prototype PTEs representing that this security directory exists. Okay? Therefore, even though the loader is smart enough not to load the security directory, because all it is digital signature information, which is not interesting once the binary is executing. It's only interesting at load time. So in older versions of the OS, artifacts of that are left in memory in the form of these prototype PTEs. So we know to go to disk and get them and feed them into our hashing function. Everything works. However, on Windows 7 and Windows 2008, surmise, the security directory is not represented by any artifacts in the prototype PTE array. I don't know why they got rid of it, but they did. So in order to make up for this, we'll have to parse. We have the PE header in memory, right? We found it through this file object. Once we read it, we can see if it has a security directory associated with it, so it has a digital certificate or it doesn't. If it does have a security directory associated with it, what we'll have to do then is use the relative virtual addresses and so forth of that security directory within the PE file and go to it on disk at the end of our hashing and feed that back in. Once we do that fix up, the hash will match again. So those are the two caveats that we ran into thus far. I don't anticipate any others. It seems to be working okay. Here's the references. If you're interested in how all this stuff works, you can read through those references. If you're interested in some of the other tools that do memory analysis, they're referenced there as well as in the paper. We'd like to thank Peter Silverman and Jen Andre for their work in gathering some of this research for us and applying some of the filters and so forth. And now we'll take questions.
Can you maybe talk about how robust this is across Windows, or including some releases of service packs, something like this, and getting these constructors? Have you seen that it changes a lot?
No, we've built it in for every version of Windows since Windows 2000. So we have, the structures change a little bit, but we've accommodated for that. So we have it working on every version.
How much does it change? So you say a little bit, but it doesn't change very often?
Yeah, it doesn't change very much. It's more or less, the members are the same. It's just their location within the structures that we're finding move a bit. And if you go to Matthew Sweet's Moonsouls website, he's broken down, he's basically used Windybug to dump out the structures for pretty much every operating system that you want, except for Windows 2008. Please add that, Matt. But anyway, he'll break out the structures for you, so he'll tell you where the offsets are, basically. Also, if you were using that, you have to take into consideration, there was one place in there where I talked about an array of prototype PTEs. Well, prototype PTEs on a 32-bit system that's non-PAE, so physical address extensions, are obviously 32 bits. On a 32-bit that is PAE enabled, or a 64-bit system, every entry in that table is 64 bits. Any other questions? So the question was, will Memorize or Redline work with the new Memorize? It currently does not. It will need to be updated. Redline, for those who don't know, is also one of our free tools that was developed by actually our UI programmers at Mandiant, and it still uses Memorize as the engine to do memory analysis, but it's a little bit cleaner, sexier interface. Something that Peter didn't write. But anyway, it would have to be updated. That would be probably several months down the road, just because we're trying to get some other features into it that are more important to us right now. Anything else? The MFT structure? I think it is there, but I haven't done much research in it. And when all the processes that we've acquired haven't dumped that magically out. So it may be just a fixed location, or maybe actually in the file cache or somewhere. So we'd have to look into that. Anything else? That's a good question. So driver discovery and memory, the tools will do it for you. Memorize and AutoViewer will do it for you. We don't have any slides about it. I don't think we've presented at a conference. There's going to be a workshop, I think it's tomorrow, by one of the guys from Volatility. He may cover it. I'm not sure about that. Anyone else? In the back? Have I looked into doing something like this on Linux? No, not yet. Just, it's basically a resourcing issue at this point. Anyone else? All right, well, glad you came. Hope you enjoyed it.